Greetings. Dr. B here to talk to you a little bit about statistical hypothesis testing. For those of you who are following along with my textbook, I wrote a textbook along with Hal Keese on statistical concepts for the behavioral sciences. This is chapter 8 of that textbook. So you can see we're talking about statistical hypothesis testing. And as we get into this, we have to stop and think, like, what is a statistic, right? A statistic is a number that we use to describe what's going on with a sample. What is a hypothesis? It's a prediction about the relationship between two or more variables. What is a test? We're testing the hypothesis using statistics. And so statistical hypothesis testing is one of four primary uses of statistics. The first one being descriptive, that we use to describe what's going on in a sample. The second one, inferential, where we use a sample to draw conclusions about what's going on with a population. This one is hypothesis testing, where we generate a hypothesis, we generate a prediction about the relationship among variables, and then we gather data and we test it using statistical hypothesis tests. And the last one is finding associations, which actually is at the root of AI. But today it's statistical hypothesis testing. And now we know what a statistic is, we know what a hypothesis is, and we know that we're doing a test. There's two primary categories in statistical hypothesis testing. We have parametric tests and we have non-parametric tests. So parametric has a word that you probably have heard before, right? Parameter. And what is a parameter? A parameter is a number that characterizes what's going on in a population. And we have lots of parameters that we talk about. Typically, the big ones are mu and sigma, right? Mean and standard deviation. But there can be other parameters as well. And so anytime you're doing a statistical test using a sample to test what's going on with the means and the standard deviations, you're using a parametric statistic. Non-parametric statistics or non-parametric tests don't start with parameters. They actually do something else. They're still giving you a sense of what's going on. You're still testing a hypothesis. They're a little more complicated to understand, but they once you understand parametric tests, it's pretty easy to move over into the non-parametric space. And non-parametric statistics are actually easier to test. So let's walk through our parametric tests a little bit here. So the key to a parametric test is that it is a hypothesis testing test. So you start with a hypothesis regarding a parameter, like mean or standard deviation. Right? So you start with a hypothesis. You make a hypothesis. You make a prediction about the relationship among two or more variables, maybe two or more means, um, and and that gives you your start to your parametric test. From that, what you're going to do is you are going to gather, design a research approach to collect the data. And this particular video is not about research design. There are other videos that you can watch on my channel about research design, and more will be coming, but this one's about the statistics. So we're going to pretend like the data have been collected properly and we're in good shape here. So we collect the data and then we calculate the statistics, right? And so these are the general broader steps in parametric statistics. You start with a prediction about parameters, and uh, parametric statistics works best when the population from which you are drawing the sample is normally distributed. These kinds of statistics tend not to work when you have a population that's not normally distributed, like that's skewed, maybe like income data. You would not do any parametric statistics testing on income data because it just simply is not normally distributed, right? We have people down here, and then we have far fewer people off to the side in the tail. And this kind of statistic is not going to work. Parametric statistics are more powerful than non-parametrics. But the challenge is that there are these assumptions that have to be met for it to work. Like that the population from which you're drawing your sample is normally distributed. And we already know that the most data that we're interested in, particularly in psychology or in the space of educational improvement or advancing issues with justice, involve people. Anytime we're talking about humans, most of the time this data are not normally distributed or even close to it. And when that happens, you have to move over to the less powerful non-parametric statistic, which means even if there's a real difference going on, even if your hypothesis is correct, you're going to be less likely to find it just simply because of how statistics works. So, but you do not want to be using parametric statistics if you're not meeting these assumptions, like the assumption of normality. And as you learn more about each of the statistics, each statistic has its general assumptions that need to be met, but all parametric statistics have the assumption of normality. There's another assumption that they all have that we'll talk about in a little bit. So here we have our non-parametric statistics. So what about our parametric statistics? What about our non-parametric statistics? So in this case, you are generating a hypothesis, but a parameter is not involved. I'll give you a perfect example. Let's say I noticed an interesting pattern in my advising data. So I have a whole bunch of students who come to me for advising, and I have two male students in that bunch right now, and a whole bunch of females. Now, part of that is because I advise psychology majors, and psychology majors are overwhelmingly today female. That hasn't always been true. Back in the day, they were overwhelmingly male. And so now understanding some of these gender differences might be important. We don't want to make psychology exclusive to just women. So doing a test, like trying something out and doing a test to see, is there a differentiation between males and females? We're not talking about means here, right? We're talking about more of a differentiation. This would be an example of a place where you would use a non-parametric statistic, specifically a chi-square. But the other place that you would use a non-parametric statistic is you're going to use it when the assumptions for a non parametric statistic are not met. So we already talked about one of the assumptions, and that is normality, that the data from which you draw your data, like the population from which you draw your data is normally distributed. And we know that there's a lot of data that's not normally distributed, like income data, but also attitudinal data. If you were doing research on, all right, so we've been talking about let me do this. Okay, so we've been talking about the primary types of hypothesis testing statistics. Let's start diving into some of this terminology so that we can all be on the same page. So again, we have this idea of a hypothesis. Now, most of when we've been talking about hypotheses, typically till this point, it's been about a research hypothesis, right? And a research hypothesis is first and foremost a prediction about the relationship among two or more variables, right? And so I'm going to start with a hypothesis that I have. My hypothesis is that students in statistics get better grades and thus understand, or actually, I should say, they understand the material better, which leads to better grades when they engage in effective studying. That is 1 hour a day, 6 days a week. My hypothesis includes taking a day off is helpful, but that you want that steady, every day, 1 hour a day studying in statistics. And so that's my hypothesis. And so as I'm recording this particular video, my classes just took their second exam for statistics. And I was excited. The mode There was a bimodal distribution of 105 and 100. So a lot of students did really well. In fact, there were as many students with a grade of 90 or above as there were students with grades of 80 and below. So, generally they did well. The problem is that when the students did poorly, which started at around 85 or below, it was very obvious for me to see why. They were missing foundational principles that if they did their homework as assigned, there's no way they would have gotten it wrong. It just wouldn't have happened. And so my hypothesis is that I have one hypothesis, that is that the 1 hour a day, 6 days a week is going to yield better understanding in statistics. But here's my challenge. I've been telling my students that it's in my syllabus. I announced it on the first day. I've sent them emails. I've had discussions with them, and there are still a little less than half of the students who aren't doing the work. So I've come up with another hypothesis. So I know that my students are busy. I know that they have conflicting challenges going on, and I know that they have a lot of stress in their lives. I also know that learning statistics and graduating from college is going to address a whole lot of those issues by enabling them to make more money in a job, and statistics in particular. That statistical skill will get you a decent job and also keep you from being fooled into things by people who are trying to use numbers to lie. So this feels like a really, really good thing worth investing time in. But to date, my ability to convince my students, at least about half of my students, to behave effectively has been inconsequential. So I have a new hypothesis. My hypothesis is that if I have students reflect back on one of their ancestors, somebody who's at least 3 generations behind, right? Maybe a great grandma or somebody before that. And I want them to think about one of their ancestors, just one, get one ancestor that they could kind of envision in their mind. Of course, it won't be somebody that they probably have met. likely, but that they can envision that ancestor in their mind and what they ate, what they drank, what their house was like, how they protected themselves from excessive heat or excessive cold, how they protected themselves from danger. And what were some of the things that they worried about? What were some of the things that they aspired to? And I want you to think about that ancestor right now and think about what do you think that ancestor would think of the opportunity that you as a student have right now in college? How excited would they be? How would they feel about how their sacrifices have led to this moment in time right now? And then what would they think if they knew that you were not following through with the very work that you need to do that only takes time, not money, for you to accomplish so that you could be successful, truly successful in this space? How would they think? What would they feel? What might they say to you? And so my hypothesis is that by reflecting on an ancestor that and the sacrifices that that ancestor made and the gift that current college is for that student, that it very well might motivate them to behave in a way that we know straight well is increases grades, right? And so that's my research hypothesis, right? And the research hypothesis is that prediction among the relationship between two or more variables, and it's explained in words. Well, statistical hypothesis testing is, yes, testing a research hypothesis, but it's doing so through first creating a statistical hypothesis. And a statistical hypothesis is a statement about the population for a parameter, right? We're going to talk about parametric statistics right now. Is a prediction about the relationship of a population parameter, right? It's a statement about the relationship of population parameters. And so in my example, a perfect population parameter would be a student's grade, the mean grades, right? So the arithmetic average is the mean. So mean grades in this case. And so we're going to make a prediction about the mean grades. Okay. So this is our statistical hypothesis. Let's come over here and start drawing what that looks like. So there's technically two statistical hypotheses. Let me undo that. Can I erase you? No, we'll just pretend like it's erased. Okay. There's two statistical hypothesis testings, right? There's one that's called the null, and thank you for appreciating my junky draw handwriting. It would be the same if it was on the chalkboard. So there's that. But there's one that's called the null. This is the null hypothesis right here, right? Null means nothing, right? Null and void, nada, null, nothing going on, right? So in the null statistical hypothesis, you're saying there's nothing going on. Telling students about the story and getting them to be self-reflective about their ancestor is going to have no impact on their grades, right? So if we had two different groups of students, one group, right, we'd call it group one, and the other group, we'd call it group two. We would get mean scores from each of these groups. And so this is the group that heard the reflection and started to reflect about their ancestors and what their ancestors would think and feel and what would they think of this opportunity that a college student has that they sacrificed for, and they're, not fully leaning into it with studying a mere 1 hour a day, 6 days a week for their statistics class. What would they feel? So we take our research hypothesis, we turn it into a statistical hypothesis, and now what do we do next? Well, we know when we're collecting data, right, that we have sampling error. Right? The participants who just happen to be in our sample are bringing sampling error with them. That is error due to the individual differences of the participants who just happen to be in our sample, right? And in our particular study, think about all of the different types of sampling error that the students might bring into a statistics class, right? Some students are really excited to learn statistics. I know for those of you who are not excited about it, it's hard to imagine, but some students are really, really excited to learn about statistics. Some students are bringing mathematical baggage with them, right? They've been told that they're never going to be good at math, and they're a little apprehensive of that, and they might have some math fear and anxiety associated with it. Some students are coming into class and they're in Calc 2 already. Maybe they had AP statistics even in um, high school, or they had statistics in community college before sitting in this class. And then there are other students in this class that are struggling to figure out how to use their calculator. And you know what? It's all okay because they can all learn statistics. But it definitely makes for learning statistics a little bit different, right? And so everybody brings in this sampling error. And so we go and we take these measures and so there could be other things, this other sampling error masking it. Well, this is where the sampling distribution of the means come in, which is super, super cool. So as you probably recall, the sampling distribution of the means is a way for us to go about getting a sense of um, how much sampling error there is in our mean, right? And so if you remember, the sampling distribution of the means is a distribution, it's a graph of sample means of the exact same size n, and ignore the little arrows. I don't know how to turn them off. Exactly the same size n, and you grab a sample, you graph it, you grab a sample, you graph it, you grab a sample, you graph it, and you graph every single possible sample that ever could possibly be out of this population. And thanks to the central limit theorem, it gives you a perfectly normally distributed sample, which means you know that approximately 30%, 34% of the scores fall between the mu and sigma, right? But in this case, we're not talking necessarily about sigma because these are not observations like in a normal distribution. This is the sampling distribution of the means. So here we get our sampling error, right? So we will have -1. There's our standard error, which is a measure of sampling error. We have +2, standard error, right? And so forth and so on. And so as a consequence, we have this measure of sampling error, right? Error due to the individual differences of the subjects that just happen to be in our sample. So Picture, if you will, I have lots of data from the 20 years that I've taught statistics. And I only just came up with the idea that, hey, maybe it might help students to study more if they reflected upon their ancestors. And I thought about this because I often think about how my parents and grandparents in particular sacrificed. And I did get to know my grandmothers, great grandmothers, and how they sacrificed in order for me to have a better life. And none of them went to school. And so when I was in college, I really wanted to make the best of the situation. And so I thought, well, maybe I'm going to try to have my students do the same kind of reflection. And the reason why I want to go further back is because a lot of us have trauma with the generations that are currently living. And so we want to get back past beyond and think past beyond the sacrifice that was made by people that we don't necessarily have direct trauma from. So here we have our sampling error, and so imagine I have all of this data on how students do in this class, and I take a sample and I take another sample and I take another sample and I graph of the same size and I graph the sampling distribution of the means, right? And we have a mean score for how students typically do. And the how much variability there is would be the standard error, right? So now I run my study and I'm going to get a sample mean, right? So let's say I take 30 students, right? And so I have this, actually, let's say 40 because normally my class sizes were 40 anyway. So I have 40 students. I've collected the data for sample, generated the sampling distribution of the means, and it gives me a sense of where each of the means fall. So yeah, I grab a mean and nothing's going on. So I take a group of students and I get them to reflect on um, their ancestors, see if it changes their study behavior, which increases their student learning, and go with it, right? And so I grab this mean, and if we assume that the null is true, right? So we start with the assumption that the null is true. We're going to get the sampling distribution of the means. That's what we're going to get. If the null is true, nothing's going on, and most of the score samples are going to have the exact same mean as the population. Very few will have very extreme scores. Some will be close. It'll be random. Some will be a little above, some will be a little below. And because of central limit theorem, you get this perfectly normally distributed property. So when we do hypothesis testing, we have to start with the assumption that the null is true. And from that, it enables us to generate the sampling distribution of the mean. Now, before I go any further, a lot of people struggle with this idea, the assumption that the null is true. But you make assumptions every day that you go into. An example of one is that you assumed that your university would have a program that would work well for you, and you had to make an assumption. Lots of students start off at the university in a particular degree, and then they get there and they're like, oh, wait, my assumption was wrong. You get evidence and you're like, no, 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 this wasn't the right place for me. This isn't the right degree. And you either change degrees or you leave the university and go someplace else, right? But you wouldn't have even entered in to college if you didn't assume that this was a decent place for you and it was the right major. This is also true a lot of times with dating, right? We're not going to start dating a person that we don't think is going to treat us properly and that we might have fun with, that they share our values, these different characteristics that you go like, okay, fine. I think this person has enough of it going on. I'm going with the assumption that this person is worth my time, right? And you go out on a date. And sometimes things happen, right? And things don't go well. And you have to sit there and go, was that just a fluke experience, or is this a real, problem with this particular person, right? Was it just a bad moment, or is this a sign of worse things to come? And so you grab data, you grab data, you grab data, and over time, there comes a point that, there's going to be some variability. And you're going to expect that. You're not going to expect a perfect date every single time. You're not going to expect a wonderful experience single time. Sometimes it's going to be like a little blah, right? But you're going to draw a space where you're like, you know what? At this point, um, anything that is beyond this in this extreme space here, right? Anything that's in this extreme space is just too much. I can't do it. This isn't just a little minor flaw. It's too much, right? So at that point, what you do is you start with the assumption that the null is true, that this person is worth going out with and spending time with. But then you determine, hopefully before you start going out, what is the point where you're going to reject the assumption that the null is true, right? You're going to reject this assumption that the null is true. You're going to say, you know what? Nah, I know, I think it's okay, but nope, it's not okay. There's too many signs, and I have to say adios. I have to say goodbye, right? It's too much. And when we get a piece of data, a piece of evidence that throws us in that space, then we like, you know what, this is too much. And we have to figure out for ourselves what we consider extreme enough, right? We get to decide, not anybody else, whether we're dating or whether we're doing research. We get to decide what's the point where we're going to reject, right? What's the region upon where we're going to reject the assumption that um, the null is true. And once we have that sense of what that rejection region is, now we can go and, oops, give me a second. Now we can go and get our sample mean, right? So we're back to the space where we've gotten a group of students. We've taken them through the imaging training to see, does this improve their long-term success in a statistics class? And we get a mean. We get a sample mean, right? There's subset of the population that have received this specialized treatment, and we get a sample mean. And let's say our sample mean is comes out to an 88%, right? Well, now we're going to take this on to our sampling distribution of the means and ask ourselves, um, is this, does this make sense? Like, what is our mean? So let's pretend our mean is an 85, right? Well, clearly 88 is higher than 85, but in our sample, we have sampling error, right? We have error due to the individual differences of the subjects that just happen to be in our sample. Maybe we ended up with an extra group of students who took AP stats already. So they already had statistics under their belt before they even started this class. And so of course the mean's going to be higher in that particular case. And so we have to figure out, is the difference between these two means real, because of the impact of the training? Is it a real difference or is it a chance difference, right? Let me write that down. We're looking at, is it a real difference? That is the difference in the mean is because of the treatment effect and goes beyond sampling error? Or is it a chance difference, right? Is it a real difference? Oh, sure. Or is it a chance difference, right? In the case of a chance difference, this is just error due to the sampling error, right? This is just sampling error. It's just the chance of who happened to be in your study, right? And you're not going to know off the bat whether this 88 is due to sampling error or due to a real difference until you calculate a statistic. Well, here's the cool thing. So we need a few more things about this here. So we already know what mu is, right? I'm going to break this over here. Mu equals 85. And we already know what n is. I'm actually going to change the number of n because I want to be able to do a nice, easy square root. So let's do 25. So our sampling distribution was done with n equals 25, and this sample has 25 people in it. It's all good. We know that the sigma in this case is 5. Okay. And so in order to get everything that's going on here, we need to calculate the standard error. And the formula for the standard error is sigma, which we know is 5, divided by the square root of n, which we know is 25. And so that gives us 5 divided by the square root of n, the square root of 25. Let me put that in there. The square root of 25 is 5. Thus, the standard error ends up being 5 divided by 5, which gives us 1. All right, so if 85 is here, we're going to add a standard error, which is 1. That's going to make this 86. We're going to add a standard error, which is 2. That's going to make us 87. We come over here to our third spot. That's going to be 88. We're going to come down here. This would be 84, right? We're taking off a standard error this time. We're taking off another one. This is going to be 83. This is going to be 82. So I drew my point where, and I'm sorry that my distribution isn't fully symmetrical, just pretend it is. I drew my area where I'm like, you know what? If it falls beyond this point, I'm going to say the evidence is too extreme that I can just assume that the null is true. So to bring it back to the dating, right? You're going out on a date, everything's going well, and then a person mistreats the wait staff. And you're like, you know what? Nah, we're not doing that, right? This is too extreme behavior. If you're going to be disrespectful to a server, you don't have respect for people. And I need to be with somebody who has respect for people. And you just go, bye-bye, I'm done, right? The behavior is too extreme. That's not something that, maybe if somebody's just a little snippy or upset or, they had a bad day, fine, you can let that slide. But being completely disrespectful to a server, nah, no, you're not going to let that slide. And so it falls in this rejection region. Well, for statistics, where we like to keep things is one of the places, and another video will explain to you why, or another class will explain to you why. But we like to keep this point where, you know what, I'm going to say 95%. We're going to have this wiggle room in this 95% space. And if it's in this 95% space, we're going to consider this normal. Yeah, sometimes the behavior is going to be a little above, a little below, but it's going to average itself out. And we're going to consider this middle 95% normal. Well, that means that we have 5% left. We have 2.5% on this side and 2.5% on this side. Now, if something falls in these spaces, even in psychology, we consider that pretty rare. We consider that enough evidence that we're going to have to disregard the null hypothesis, right? We're going to say, nope, if it falls in the rejection region, the null hypothesis is not true. It's not true. Well, if the null is not true, then what's true? That means the hypothesis, we're going to accept the alternative hypothesis. So we reject the null. We reject the null. We say it's not true. And then we accept the alternative, right? We accept the alternative. In this case, that the means are different. And in our example, that means that the reflection did have an impact. And we know that with this 88, it shows up right there, right? We can see the 88, so we know we can reject the null. But not all numbers are always going to be that great. So what do we need to do? Well, we learned previously about the z-score. The z-score tells us the location of a sample mean on a sampling distribution of the means, right? That's what a z-score tells us. And so if the z-score can get us that location of the sample mean on the normal distribution, we can compare that location with our rejection region, right? And if the z-score falls in the rejection region, we reject the null hypothesis. And if we reject the null hypothesis, we accept the alternative hypothesis. This becomes statistical evidence that our treatment had an effect, right? If we reject the null hypothesis, we're no longer accepting that the means are the same. We're saying the means are different, and that difference is real, not chance. It goes beyond sampling error. There's too much evidence to say this just happened by chance, right? There's too much evidence to say that this just happened by chance. The difference is real, and the treatment had an impact, a real impact, a real effect, right? So we're going to reject the null and accept the alternative. Well, you know how to find the z, right? The z you already learned how to do. This is pretty simple to do, right? The z is the sample mean minus the mu divided by the standard error. And this is your first hypothesis testing statistic, right? We're asking ourselves, is there a difference between the means? Is there a difference between the means that goes beyond sampling error, right? Standard error is a measure of sampling error. Is there a difference between the means that goes beyond sampling error? And here we have it. So we can calculate our mean. In this case, we had a 88 minus an 85 divided by the standard error, which was 1. Oops, scratch it out. Just ignore that, which is 1. So we have 3 divided by 1, and our z-score is a positive 3. Z-score is a positive 3, which is going to fall right here in our rejection region. So the only thing left to determine is, how do we determine our rejection region? Well, we know approximately 5% of the population is above 2z and below 2z, right? Above positive 2z and below negative 2z. The exact value is plus or minus 1.96. This is the exact, and you can go look it up in your standard normal distribution. And so it's not exactly on 2. It's a little smidgy below 2 where our actual rejection region starts. But that's how this has worked out. So the question is, how is it that we end up picking this 2.5% on either side, right? The 5.5, the 5% that's been split. This actually has a symbol. It's called alpha. We're going to learn more about alpha next week. But for right now, just know that alpha is what's called our significance level, right? Let me do this. Alpha is our significance level. And we select it. Typically in psychology, we select it at 0.5, but the truth of the matter is that we can select alpha at 0.0. I mean, I said 0.5, I meant 0.05. We can select alpha at 0.01. We can select alpha at just about anything. As you learn more about statistical hypothesis testing, you will learn why psychology settled on 0.05 as their alpha. So that's saying that if the data are so extreme that it's only going to happen 5% of the time if the null is true. So we start with the assumption that the null is true, right? Just like you start with the assumption that the date's going to be a good one. Things are going to go, there's going to be good and bad. There's going to be a little bit of stuff that happens, right? Humans are humans. But you have a point where, look, if this behavior is so extreme, here's my significance level. You cross into the rejection regions, I'm saying bye-bye, right? And that's exactly what happens here. You are establishing a point where you're like, look, I know there's going to be sampling error, and I'm willing to take a bit of sampling error. But if it's too extreme, I'm not going to believe that there's sampling error. I'm going to say the null is not true. We're going to reject the null. Here's the thing. You could be wrong. Even if nothing is going on, you're going to reject the null. What percentage of time? 5% of time. So this is why statistics, this is why psychology, we never prove anything, because we know we can reject the null 5% of the time on our best days. So we never prove. We keep on testing, we keep on refining, we keep on moving forward, but we never prove. All right, this is a lot. And as you're watching this video, you may want to pause it and come back to it a few different times. But we are now going to go to one more thing. Okay. So our sampling distribution of the mean works really, really well as long as we know our population parameters, right? Our mu and our sigma. And there are some times when we know the mu, but we don't know the sigma. It doesn't happen often, but I'll give you an example of a research time when it happens. And one of the things that studies that I've done with students in the past, and it always, always, always works, is I ask them, how bothered am I when students are late? So right now, for my students who are listening to this, come up with a number. How bothered am I when my students are late on a scale from 0 to 10, 10 being extraordinarily bothered, 0 being not bothered at all. Okay. Now, most of the time, so here's the thing. We know what my belief is. I know what my belief is, right? My belief is the mu. My belief is the truth, right? That's the standard upon which you are comparing yourself. And we're rating this on a scale from 1 to 10. I think I said 0 to 10, but we're going to go 1 to 10. 1 is it doesn't bother me at all. 10 is it bothers me tremendously. And most of the time, what ends up happening when I do this study is I select 5 students and I grab a sample, mean, and keep in mind, I already know what the mu is, but I don't know what the sigma is. And I get a sample mean, and the sample mean is typically somewhere around 6, let's just say. Students are like, yeah, it bothers her a little bit, but not that much. And then the standard deviation, there's normally not that much of a standard deviation, but normally there's a standard deviation of, let me just stick with a standard deviation of 1. Okay. And so um, normally that is, and uh, let me move this up. Actually, I'm going to um, do an N of let's stick with an N of 4. I know I said I normally do 5 students, but let's just do an N of 4. Okay. So the first thing I have to do is I have to calculate my standard error, right? But in order to do that, I need this guy right here, this population standard deviation that I just butchered. And then divided by square root of n. Well, I have the square, I have n, but I don't have this. So what can I do? Well, I can estimate the standard error. And when we estimate the standard error, the formula is going to be pretty similar. It's divided by the square root of n. What do you think goes up here? And that's right. The standard deviation that you estimate goes up there. So in this case now, I have 1 divided by the square root of 25. I mean, the square root of 4, which gives me 1/2, right? And I have my sample mean, and now you need to know what is my population mean. My population mean is actually a 9. We'll get that right there. It bothers me a lot. I understand that students are going to be late for various reasons. You have caregiver responsibilities, your car breaks down, you make a mistake, but it bothers me so much because the beginning of class is when your mind gets prepped. And when you miss the beginning of class and you come in even just a few minutes late, you're not learning as much from that class period as you would have if you got to class a couple minutes early and got yourself ready to learn. And we're at the beginning of the class. And so it's interesting research that was done and published by ESU students several semesters ago with a professor called Dr. Wesp, found out that students, college students, do a very, very poor job of estimating professors' attitudes on all kinds of topics. They just do a very, very poor job of estimating it because they rely upon signs that they think like if a professor doesn't yell at you, they that means that they're not upset by it. But if I were to yell at every time a student came in late, I'd disrupt the class and I'd disrupt your learning, which would make things worse, which is why I don't yell. But I definitely don't like it. And because it interferes with your learning. It doesn't interfere with my teaching, but it interferes with your learning, and that's a problem. So here we have our sampling distribution of the means, right? But this one's going to be a little bit different because it's not the standard normal distribution because we don't have this. We can't draw it out. Instead, this is called a T distribution, right? Let me do this. This is a T distribution. And a T distribution on the surface looks very much like a normal distribution. It actually gets really close to a normal distribution when the population size is really big. So not the population size, the sample size, when you get a really, 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 really big sample, a T distribution will um, approximate a normal distribution. But absent of that, it's not going to be quite like that. But the T distribution still is set up very much the same, right? And so you have your mean, right? And you start with the assumption that there is no difference. In this case, the null hypothesis, right? Or null hypothesis is that the means are the same, that my mu, how much it bothers me, and your understanding of how much it bothers me, that you're late, is exactly the same. And we start with that hypothesis. We generate the T distribution. And in the T distribution, instead of us having the sigma x bar, the standard error, we're going to have this kind of standard error, an estimated standard error, right? And this gives us our T's coming this way. And we start to say, okay, there's going to be a point where the data are so extreme that we're just going to reject, right? We're going to reject it. If we collect the data and we we calculate the t-test, and we go with the assumption that the null is true, we're going to have this area that we're going to mark off as, yep, if the t-test falls in this area, this is too extreme. We can't just say it's because of sampling error. We can't just say it's because of chance, right? We are going to say that this is too much for us just to ignore it. And so we're going to reject the null, and that means we're going to accept the alternative, which means the means are different, right? In this case, that your belief does not match my belief. And so you generate your rejection region, or you generate your T distribution, you identify your rejection region. And the way that we do this is a little different. So we know with the standard normal distribution, if we have alpha equals 0.05, we know that that rejection region is going to be plus and minus 1.96, right? We're going to stick with alpha equals 0.05. Again, in another lesson, you'll learn why psychologists like alpha equals 1.105. But we need to find the rejection region. So we're going to go to our handy dandy book. And this time, instead of you're going to Appendix C, all the way in the back of the book. But the last time we went to Appendix C, we looked at that table, right? The standard normal table, when we were finding the location, the probability of where something fell on a standard normal distribution. right? But now we're not using the standard normal distribution. We're not using the sampling distribution of the means. We're using we're using the t-test. So we're going to go to the t-distribution. And if you take a look, so right now, if you're watching this video, pull out the t-table. You're going to see that on the t-table, you have some decisions to make, right? There, one decision is whether you're going with a two-tailed or a one-tailed test. Now, I'm going to explain later why we always go with the two-tailed test and why a one-tailed test is cheating, but we're going to stick with the one-tailed test. You also get to choose alpha. In this table, you can choose alpha as 0.05 or 0.01. Again, in the future, I'll explain why we do 0.01. So we're going to do 0.05. So now there's this other space, and don't let this table get scary to you, but it says DF. DF. DF stands for degrees of freedom. Now, later on, I'm going to be, because we've just covered so much stuff, I'm going to explain to you what degrees of freedom means, but not today. For right now, what you need to know is for that each statistic has its own degrees of freedom, and you'll normally find the degrees of freedom written with the statistical formula. So if you go to your book and you look up the different statistics in your book's cover, you'll actually see that it has the degrees of freedom. For this t-test, the degrees of freedom are n minus 1. So in our example, n is 4, n minus 1 then is 3. We're doing a alpha equals 0.05 two-tailed test. So we come to our table, right? We come to our table. We're going to go with alpha equals, we're going to go with a two-tailed test. We're going to go with alpha equals 0.05. Hopefully I'm pointing to that properly. We're going to come down to our degrees of freedom for 3 and follow it over, right? And if we do that, our t-test is score is 3.182. So, oops. Let me do this one. So 3.182. On this side, that's going to be negative. And on the other side, it's going to be positive. So that's positive 3.182. All right. And so what that means is that when you calculate your t, if your t falls above positive 3.12, it's falling in the rejection region. You're going to reject the null and accept the alternative. If it's below 3.182 and it's falling there, it's falling in the rejection region, you're rejecting the null and accepting the alternative. So that leaves us with calculating the t-test, and we need to know what the formula is for the t. Well, the t is just like the z, where it's asking, is there a difference between the means? Right? Is there a difference between the means? So that stays the same. That goes beyond sampling error. So let me write the z-test right over here for right now, right? So remember, your z-test is asking you, is there a difference between the means? That goes beyond sampling error, right? But you have an exact calculation of sampling error because we know the standard deviation in a population like this. But there are times that you're not going to know that particular parameter. In fact, most of the time, you're not going to know that particular parameter. So we used this as an estimate of the standard error. And that just goes right down here. So in our example, we have the mean equals 9, mu equals 9, sigma equals, sorry, let's try that again. So in our example, we have the mean is 6 minus 9 divided by our standard error, which is zero 0.5, right? 1/2 equals 0.5. I should have done that over here earlier. So that gives us -3, right? Divided by 0.5, which is actually -6t, which is going to fall like way down here, which is definitely in the rejection region. But give me a second. All right. I finally was able to figure out how to use the eraser on this version. It's interesting, just the complete side topic, because I haven't given you any side stories all day today, so you need one. Back during COVID, when I was teaching this class, and I had to switch everything to online, and I had no problem using the Zoomy thing then. The board was different, and of course with practice I got better. And you can even see in this video I haven't used a whiteboard probably since 2020, and you can see already just in this video that I've gotten better from the beginning to the end. That's what happens. You practice, you get better. That's true about writing. That is true about using um, a whiteboard or technology like Zoom. That's true about statistics, right? And I don't expect you to be perfect, just like you don't expect me to be perfect. But I do expect you to try, and I do expect you to work hard, and I do expect you to be successful, because the world needs you to be successful. Your family needs you to be successful. And 2 or 3 generations from now, there's going to be somebody who's going to be so grateful that they're in the position that they're in because of choices you are making today to better yourself through education. So we've covered a lot in this video, and we have talked about statistical hypothesis testing. We have the statistical hypotheses, the null, the alternative. Um, when we go with our testing, we are either going to use the z-test or the t-test. Right now, we use the z-test if we know sigma. If we don't know sigma, we use the t-test. But other than that, they function the same, right? We start with the assumption that the null is true, and we generate a sampling distribution. We identify the rejection region where we're like, nope, this data is too extreme for us to just accept that the null is true. We're going to reject the null and accept the alternative. And when that happens, then you know that you are saying the treatment had an effect. In the case of our example, that reflecting on your ancestors improves your performance in statistics. Now, I've never studied that, so I don't know if that's true or not, but it seems like a question worth looking at some particular point. So you mark off the rejection region, then you collect your data, then you calculate your standard error. If you know the sigma, you calculate this standard error. If you don't know the sigma, you calculate this one. If you're calculating this standard error, you can use your z-test. If you're using this standard error, you're going to use your t-test, right? And if the z or the t falls in this area, you fail to reject the null. Now we're going to dive into why you don't just accept the null later, but for right now, you fail to reject the null. You just like, and it's just like when you're dating. You had a good date. That doesn't mean that you met the right person yet. It's going to take a lot of dates before you have enough data for where you're like, okay, yeah, I met the right person. And this is the person for me permanently. So you can have a great date and you don't go, yeah, let's go get married. I mean, I've known a couple of people who've done that, but don't do that. You need a lot of data before you can move forward. So we fail, it's in this space, we fail to reject the null, but if it falls in the extreme, then we reject the null and accept the alternative. And we say, look, this is not because of chance difference. This is a real significance that the treatment is having an effect. So, Dr. B here with your lesson on statistical hypothesis testing. This is chapter 8 of my book and called Statistical Concepts for the Behavioral Sciences, co-authored by Dr. Hal Keese and myself. And I do hope that you have a great day. And for my students, it's now time for you to dive into the assignments and exercises and start working through those. Once you get through those, dive into the book, read the book, do the assignments that are within the book. And you should have more than enough time to get chapter 8 done by the time I see you again. You take care.